Okay, so we've seen some of the ingredients that go into these global climate models, the GCMs. And as time's gone on, these models have gotten much better. Back in the mid-1970s, the models basically had just clear atmospheres, rain and CO2. They were still fairly complicated because you had to have lots of grids around the world. You had to allow for exactly which radiation goes from which height at which wavelength. So they were still needing a lot of computer power. But as time has gone on, and if you've got faster and faster computers, and also a better understanding of all these processes, people started adding in clouds. Clouds are a really hard thing, a land surface, some ice. But initially they just said there's ice here, they didn't let it move. But then as time goes on, they started adding oceans. They started adding different sorts of pollution. They started modeling ocean circulation and coupling it with the air. They added aerosols, the carbon cycle, interactive vegetations, atmospheric chemistry and how it changes, and they've kept on getting more complicated. So the models have improved and improved and improved, and part of this is because you have better computers. Part of it is you have better understanding of all these steps. So the field researchers might work out in a grassland exactly how the absorption and radiation changes depending on the amount of rain and so on. So every step that's needed in these complicated models is subject to laboratory studies, and the models have got much better. Here's the result of a model from about 15 years ago, showing what the state of the art was back then, and it's only got better since. So what you can see is you're looking at weather patterns around the world. You're getting trade winds, you're getting easterlies and westerlies in about the right place, you've got cyclones moving past. And none of this is something you put into the model. All the model is a whole bunch of cubes and a whole bunch of laws about how things work with pressure and temperature and heat and radiation. It's still not what the real weather looks like, mostly because it doesn't have the resolution. In particular, the clouds around the tropics, thunderstorms here are very small, much smaller than the grid size of 70 kilometers on a side, and so you have to do some sort of estimate about it. You can run a model just for a small region and model these clouds, but at the moment it's beyond the world's fastest supercomputer to have enough detail to model an individual thunderstorm in the Congo and model the entire world. So they have to use approximations for that. But they've tuned these approximations fairly well. So how well do these things do? Well, there's a lot of parameters which have to be estimated because they occur on the smaller scales. As I said, the clouds are the most common one. So it might be exactly if you've got a particular temperature profile and humidity, do you get clouds? Does it form big crystals or small crystals? What's the odds of rain? You have to have tables of all these things. And to some extent you can set it by experiment, but there are some things people don't really have good measurement of exactly what size of crystals are forming in high altitude tropical clouds, for example. There's no measurement to go on. So what you have to do is you have to adjust your model so that it matches the current weather system. And the models are now pretty good at explaining our climate. They get the main weather bands right, they get the trade winds, they get the ocean currents correct. They needed a bit of tuning to do that, but you can tune these things, and there are many different rival models out there, and they tend to agree on these things. They have regular competitions between the models where they give them the same input and do they get the same output. They're not 100% accurate. They get some things wrong. For example, there's what's called the Intertropical Convergence Zone, which is a band of storms, and usually a little bit north of the equator. And a lot of the models actually produce two of these bands rather than just one. But they're getting better and better all the time, just like weather forecasting. But people worry. You've had to tune the model very finely to explain our current weather. Does that mean it's going to be any use predicting anything else? So this is where the Paleoclimate tests come in. If you take exactly the same model, carefully tuned to explain our weather today, and then put in the climate from the peak of the last ice age 20,000 years ago, does it get that right? And of course we don't know the climate in the ice age in that detail. There weren't weather satellites and stations around then, but we can measure some things like how dusty it was and which parts of the world were at different temperatures. And the models do seem to get that right. They can explain ice ages, and they do seem to predict the correct weather patterns, which where the deserts are and where the warm and dry regions are back then. For example, during the last ice age, Australia would have been very dry and very windy, and that's indeed what the models predict and what the observations actually show. So that's good. These models can explain today's weather, And they explain it in great detail. It's not just what's the global temperature, it's how does the temperature in England vary compared to that in America, how does the temperature at 1 kilometre up, 2 kilometres up, what's the typical humidity over the Sahara Desert. There's a million numbers you have to get right. So it's actually truly remarkable that they can explain something so complicated. Another test was the cooling created by the Pinatubo eruption. And when that erupted, people immediately said, okay, we predict this is what's going to happen. And it did. So that was a good test of the models. So are the models perfect? No. So if I'm being a skeptic about this, there are always anomalies. For example, this whole business about possibly having 2 intertropical convergence zones is a classic anomaly, and there are a few others. As the models get better, there were a lot of things that were anomalies 10 years ago that are not now. As the models have got bigger computers and a better understanding of all the different processes, they've gone away. There have been a few cases where there seemed to be a real problem, a contrast between what models were predicting and what was actually observed, and they discovered the observations were wrong. The theorists just couldn't tweak their models to explain the observation, and it turned out that someone had made stuff up in the measurements, which is actually a good sign. It means that they can't twist the models out of shape to explain fake data. But there is still some tuning needed, particularly of cloud physics, to reproduce the current weather. And the critics would say maybe the people probably subconsciously tuned things as a group think about climate scientists to make sure there was global warming so they can push their socialist agenda. My point of view, I think it's really hard. When you're developing a climate model, you're not saying, let's have global warming. You're saying, does a cloud form in a particular density, temperature and pressure? You're trying to explain the physics inside one cube. And all that happens is you put in the physics and the biology and the chemistry in one cube and then just run it through a supercomputer for lots of cubes all over the Earth. And the fact that that can then explain the current atmosphere at every level and all over the world is pretty amazing. And that it can explain paleoclimate data as well is also very amazing. The modelers are adjusting things like how the density of ice crystals in clouds varies with humidity, not how much warming do we want. How much warming they want just comes out as a net result. So it's not easy, even if people wanted to fudge their data to get a particular result. What about the flaws? Well, it's inevitable there are going to be flaws in models of this complexity, with grid sizes of tens of kilometres, but they are the best we can do. The critics can't do any better. They don't have any alternative to these models. They don't say how we can make better models. So we could say maybe we wait another 20 or 30 years until we have faster computers that can have flawless models. Yes, but by then it'll be too late for a lot of global warming. So we have to do the best we can, and I think these GCMs are the best we can at the moment. There may be groupthink amongst the scientists. There often is problems like this, but there's just so much data you have to match that I think it's unlikely it can explain everything.